Good morning, everybody. I'm certainly happy to be here, and thank you, Jeff, for I think it was a great introduction. I will build on what you said. It's like you said, these hydrogen times are exciting, and it's really interesting to see where we are going. I will give you basically a short overview on, let's see here if I get this thing to work, or not. Ah, there we go. All right, I'm going to keep this presentation fairly general. So I'm going to talk about, what is hydrogen. I think it's back to the basics almost. How is hydrogen produced, to give you a short overview? Where is it used? And then really, why do we need compression for hydrogen? Why talks everybody, yes, we need a compressor. And then I will talk about the different types of compressors. And just to give you a flavor, I think every application of hydrogen has pros and cons for different types of units. There's not one size fits all, one type fits all. So I will just give you a general overview where we are seeing these types of compressions are going. Then some trends, technologies that we see that are emerging for hydrogen processing, being it electrochemical, hybrid compression, linear. I talk about this new color quickly, white hydrogen, and then also a little bit gaseous versus liquid storage, dispensing, transportation, again, which also has to do with compression. So really, as I said, back to the basics, I think everybody knows, hydrogen is the first element in the periodic table. It's one of the most common elements in living things, together with the carbon, oxygen, and nitrogen. It's also the most abundant element in the universe. To think of it, the sun, 75% of the sun is basically hydrogen, and then the most of the rest is helium. So it's a great power generation that you have with the sun. It's what I also say, hydrogen is colorless, tasteless, non-metallic. It's extremely flammable, and I think Jeff alluded to that, some changes you have to do to your equipment on that. And also, it's basically a standard formula, standard pressure temperatures really is H2 and not H, and I'll tell a little bit more quickly about that. One of the things why everybody is chasing hydrogen is really, it releases a tremendous amount of energy when combined with oxygen that's in the air, and I think that's why hydrogen is really, almost the golden child these days when you look at the energy transition. So really, as I said, hydrogen really doesn't exist as single H, it's really almost always an H2. So that's what it needs to be stable. It's the smallest molecule on the planet, so it has a mole weight of 2 grams per mole versus air has 29 grams per mole. You're wondering why I'm telling you this, this is an important factor when we come to compression of hydrogen. Why do we need to compress hydrogen? Really, how do we produce hydrogen? So here are the most common ways of producing hydrogen, basically at the bottom, the ones that are probably a little bit further away from the market, while the top ones, natural gas reforming, steam reforming is probably still one of the most used ways to produce hydrogen. As you can see, electrolysis has taken over number 2 spot from coal gasification. So all these different ways to produce hydrogen really have led to this colorful chart, the different colors of hydrogen that probably everybody is familiar with. One of the things we have to be aware of, that currently still most of the hydrogen is produced using coal or natural gas as feedstock. So the bottom ones, production via fossil fuels, that's still the majority. The numbers go anywhere between 95% to 98% hydrogen is still produced that way, while the rest is done by electricity electrolysis. The disadvantage of all these fossil fuel generated hydrogen, while hydrogen itself is clean, the production emits a lot of carbon dioxide, so that's harmful to to the environment. Really, what we also have seen, what has pushed hydrogen to the forefront is when the US government introduced the Inflation Reduction Act. That really has pushed green hydrogen forward, you know, because you can get credits. I think it's now, they say, I think you get 2.6 cents per kilowatt hour if you basically have clean hydrogen that you use. Or for every kilogram of hydrogen you produce, you get $3 from the government. And I think that's, for example, while some of the things done are based on these incentives. That really has pushed that. What also has pushed hydrogen is the unfortunate situation in Europe with the war in the Ukraine, you know, where the natural gas has gone away and everybody is looking for alternative sources of energy. So hydrogen will be one of those ways. What we also can say, most of the hydrogen that's produced in the US is actually produced here in Texas or in Louisiana or in California. So those are the three leading states for hydrogen production in the US. And just a short note, you can contact Jack if you want a copy of this presentation. I'm going to make it easy on you, you know, so you don't have to take notes. You can do whatever you want to, but Jack will make this available to you just to give you a little bit more information. Next step is really, you know, what do we do all with this hydrogen? Where are we going to use it? And these are just, you know, some of the ways it's used as renewable energy in fuel cells and turbines that Jeff alluded to. Even in engines, we see more use of hydrogen being burned in engines, combustion engines. Transportation, mobility sector certainly has a big use for hydrogen in the future. Bus, cars, the opinions are a little different. You know, I think a lot of people say cars will go the battery way and not the hydrogen way. And but you have seen airplanes now are flying on hydrogen. The first test flights have been done. Steel production, certainly, where you can use hydrogen, basic chemicals, green ammonia and green methanol, green fertilizer, certainly. And then we see that certainly in the petrochemical and refinery hydrocrackers, hydrotreaters. Today, most of the hydrogen produced in the US is actually used for refining petroleum products, so it's in the refinery business, treating metals, and then also to produce fertilizer and to process food. So that's still the main application for hydrogen currently in the US. When we talk about, you know, renewable energy burning hydrogen in gas turbines, for example, you know, Jeff mentioned the blending. So blending with natural gas is certainly a way to go. I think you said the CO2 is reduced, but you also have to look at the nitrogen oxides, because you have a higher flame temperature together with natural gas. So that increases the NOx possibility and the impact on the environment. Like I said, we also have seen that gas engines basically go to 100% hydrogen burning. It's just they need a tremendous amount of hydrogen, and I will come to that too. Why is that so? Really, I guess, again, why do we need to compress hydrogen? If you remember, we said that hydrogen is one of the smallest, the lightest molecules, with like 2 grams per mole versus 29 grams per mole. So therefore, to get some energy density into that gas, you have to compress it. When you look at this chart, you see on the horizontal axis, you see basically the mass density. On a mass basis, hydrogen has about 3 times the energy content of diesel or gasoline, you know, when you look at the mass. If you do it the other way, if you look at the vertical axis, volume density, the picture reverses completely. You know, suddenly hydrogen only has about 1/4 of the energy density of gasoline. And that's actually hydrogen under pressure or hydrogen liquid. If you take hydrogen at ambient temperature and ambient pressure, gasoline basically has 3,000 times the energy density of hydrogen. So you have to do something to get this density, and that's basically why compression by any ways or means is the way to go, why everybody chases compression. That's why I have a job. At least I still have a job. My boss is sitting back there, he might tell me different afterwards. So really, that's why compression is needed. Here is another version of showing this, where you basically use gasoline as the reference point. If you are to the left of gasoline, you need more space to store it. If you're to the right, you need less. If you go up, it's lighter than gasoline. If you go below, it's heavier than gasoline. So if you want to drive a car 100 kilometers or like 60 miles, that needs 1 kilogram of hydrogen. If you store that 1 kilogram at ambient pressure, ambient temperature, it basically needs the volume of that cargo van. So really, again, that just shows you, you don't want to drive a van of 100 kilogram, but you have no space to put anything else on that thing. That's why basically compression is one of the things to get to the point where it's a useful means. So really SMRs and also electrolyzers, they only produce hydrogen as a very limited pressure. We see pressures are coming out of electrolyzers or SMRs anywhere between almost ambient to about 30 bars. And that's still not enough to really have workable energy density with hydrogen. So therefore, you need to compress it. And what you use these days is mostly either centrifugal compressors or then positive displacement. And the positive displacement can be diaphragm type or the reciprocating type. And I'll just basically go quickly into, the various things, where we see pros and cons. It's by no means probably complete, and some of you might say, yeah, this might be a little different, and I cannot argue that fact. That's the general overview as we see it, because we, for example, also make centrifugal compressors, not just diaphragm compressors. So really, the centrifugal has the advantage, it can handle very large flows, and if you remember the applications we showed before, for example, hydrotreater, hydrocrackers, where hydrogen recirculation in large quantities at very low pressure increases, that's where the centrifugal has a place to be. It's ideal for pipeline applications or even drying applications. I think even Jeff mentioned, the stuff that comes out of the electrolyzer is wet. So you also need to dry it, and again, it needs large flows and little pressure differential across the drying agent, the pressure swing absorption unit, so that's also where you can use the centrifugal. It's a reliable design, API 617 clearly says you have to be able to run it 5 years uninterrupted service. So that's what this thing is designed for. It also has its few wear and tear parts, so the OPEX is rather moderate on this. One of the drawbacks, it's really only for very low pressure ratios. Again, because you have a light gas, so if you want to basically, hydrogen centrifugal needs about 3 times the tip speed than it would need for natural gas to achieve the same pressure ratio. Now you cannot run a centrifugal at 3 times the speed, but somewhere you reach the limit. So that means you just have to put more stages in. So where you can maybe get away with 1 stage on natural gas, here you need 3, 4, 5 more. Which basically makes it more expensive, so the capex is higher, more stages makes it less efficient as well. And also centrifugals, I think some of you guys know, so anti-surge control system is needed, so the control system is a little bit more elaborate than it might be on other types of units. Now, when we talk about diaphragm compressors, their strength really is there is no linkage to atmosphere because the way it's designed. There is no contaminating of the gas that is compressed, which is very important on hydrogen, especially if you want to use hydrogen through a fuel cell. Any little bit of oil contamination into a fuel cell, it will kill the fuel cell. I think it's ISO, and the SAE norm basically says hydrogen for fuel cells has to have a 99.99% purity level. So that really means nada, no oil. And that's what this type of machine can guarantee. There is no purging, venting needed. It's very low in maintenance requirements, high reliable, and one of the big points, you know, like on positive displacement machines, which this really is the high compression ratio. You can do about a ratio of 10 per stage. So usually 2 stages of compression get you where you need to be, and these things can go up to 1,000 bar. If you want to know more about these, you know, come see us. We have a working model at our stand next door, you know, where we can talk a little bit more about why these things are what they are and how they work. One of the weaknesses, like I said, you know, because it's a volumetric machine and the size of the machine is limited, you basically only have a certain flow range that you can cover with these machines. You know, where then other types can handle bigger volumes like the centrifugal, or when I talk about the recip, you know, it's just low in flow. So it's where we basically say about 100 kilograms for a 500 bar unit, where the recip easily can do 600 kilograms an hour. Then also one of the other weaknesses, it's the capex of these machines is higher than what it is for a recip. Talking of recips, you know, certainly, again, like I said, they have their place, even if I don't like them, for good reason. But they can handle the large flows, you know, that the diaphragm cannot. Can do a fairly good pressure ratio, 3.5 to 4 per stage. Lower than the diaphragm, but higher than the centrifugal. You can have it also as a non-lubricated design, which is one of the things that you probably strive for, because anywhere you have oil might contaminate your gas. And like I said before, that's really, in some applications, you might tolerate some oil in the hydrogen. You know, it might be an industrial application. It might be even if you use it in a combustion engine, you know, they actually like some oil for their injectors. When you inject hydrogen, they might like some oil in there. But generally, that's one of the disadvantages too. If you have a looped version, you have a possible contamination. There is some non-loop versions that are basically, experience is up to about 250 bar. I know there is research and development in progress to get the non-loop up to 500 bar. I think Burkhardt, together with Shell, actually even built the test loop in the Burkhardt facility to do R&D on that. And from some of the other suppliers, we even hear that they're working on 900 bar dry piston designs. So certainly with what we see in the hydrogen market, you know, bigger is better. You know, the more hydrogen you produce, basically the lower the cost. So that's where these machines will probably push to the forefront. One of the advantages still is you have leakage of gas to atmosphere, or you have then to recompress it and bring it back to the suction. You have also, you need an external buffer gas for the crankcase to separate the crankcase from the gas side. And if you don't have nitrogen in your facility, in your process, that means you have to add something, you know, which increases your capex. One of the things also, contrary to the diaphragm machine, the unbalanced forces on these machines are higher because you basically have the gas that you compress, while on the diaphragm you do oil. So you need a higher, a bigger foundation for this. And we also see now that there is the combination of recip in the front to handle large volume and diaphragm in the back. One of the other things is the hydraulic booster, the amplifier, a very simple machine. It's very cost effective, it's limited on flow, but because it's cost effective, it has probably the lowest capex of all the machines that we have seen. So you might be able to use multiple of these for the cost of a single unit of the other types. Disadvantage, it's still, you might have contamination. Some of the manufacturers only guarantee 99% purity of these. I have been given the sign I'm already running out of time. One of the other things we see is the electrochemical compression, where you basically take hydrogen at the anode, run it through a membrane, a polymer, a proton exchange membrane, excuse me, and then you collect on the cathode, you basically collect high pressure oxygen. It has been proven in laboratory tests up to 14,000 psi, almost 1,000 bar. Commercially, we only have seen these things about 0.1 to 2.5 kilograms per hour and up to about 800 bars, so very small flows, very small units, and still, I guess, rather intensive on cost. The good thing is you have really no moving parts on this, there's no mechanical compression. The same really applies to these hydrogen compressors, where you basically use a metal that will form hydrates. It basically bonds the hydrogen to the metal and it gives off heat, and then when you basically apply heat to it, it produces hydrogen at higher pressures. So instead of using electricity, for example, you can use waste heat in your process to basically get the high pressure hydrogen that you're looking for. It's a very expensive material, it's a very heavy material. We only have seen this, actually NASA used this for hydrogen storage, not really for compression. Very low flows, 0.1 kilograms per hour currently, and about a pressure ratio of 8 if you put 2 of these in series. Linear compressors, there is basically an extension of the mechanical compression. It's an old system, so to speak. You have a movable piston, that basically uses the springs and the motor to compress the gas. You might have one of these things in your refrigerator because it has been used for cryogenic compression. So now Southwest Research has taken this to the next step on the right there, where you basically apply it to fuel hydrogen vehicles. It basically has linear motors, so it's a hermetically sealed design and very efficient and reliable. At least that's what the claim is. They're testing these things, so that might be a way to go, to have a smaller footprint. You don't have the crankcase on this, so you have less moving parts. It's more efficient, doesn't need oil. So again, that might be a good application for the future as well. Really a quick thing, the latest is in the color chart is hydrogen, because people ask, well, why can't we drill for hydrogen? Why do we have to produce it in a very energy and expensive way? There's more and more people that believe there is hydrogen that you can drill for, so that's what they're going to call white hydrogen. We'll see if that is really true, but it's, if you read this, even Advanced Research Project Agency, also a government entity. Well, government entity, I don't know if that's really a good reference, but there's people that believe white hydrogen might be a next step in the hydrogen evolution. Again, storage of hydrogen or compression of hydrogen is really, it goes back to the light gas. We need to store it, we need to compress it. You can store it either as a gas or as a liquid. And talking mostly for the transportation mobility side, we have 2 ways. You can store it gaseous in pressure tanks, 350 to 700 bar, or what we also see, you can store it as liquid, but then you require cryogenic temperatures, minus 400 degrees. So the near term for mobility still focuses on the gaseous way, while the long term, the DOE target really goes more on the cryo-compressed, the liquid way, where you basically can use liquid hydrogen. Why would you use liquid? Just here a quick overview. If you look at that football field, for the same amount of hydrogen storage in liquid versus gaseous form, the gaseous basically occupies half the football field, while the liquid side barely makes it to the 5-yard line and not even the whole 5-yard line. So really, that's one of the advantages, again, liquids. The drawback certainly is it costs money, it's energy intensive to produce liquid hydrogen. And the cryogenic is still, you know, you have boil off on these things. So what do you do with the boil off? Do you just release it into the atmosphere? What does a lot of hydrogen do to the atmosphere at the end of the day? Or you have to recompress it, which basically also costs money. I talk quickly about the mobility trend, where we see certain manufacturers really prefer now to go the liquid way. So instead of putting gas in a bottle, in a truck or in a car, they basically do liquid to liquid transfer via a transfer pump, a cryogenic pump, and you store the liquid on the car as a liquid. It's liquid hydrogen. So Mercedes-Benz, for example, for their trucks, they're following that route because they say, I get more energy into a smaller tank, into a smaller volume. And for trucks, you know, range is everything, and especially you can also refuel it rather quick. And I think my last thing is, you know, transport of hydrogen based on compression, liquefaction. You can store it and transport it as gas, as liquid, or as a chemical. Rules of thumb here, you know, small amount of hydrogen, short distance, gaseous, compression. Large amount of hydrogen, longer distance, liquid storage, for example, pumps. And then the very large amount of hydrogen, long storage duration, long distance. That's where you basically the chemical storage, where we see the different ways methanol can be used to basically transport hydrogen in ways. Ammonia is used. And really one of the other things is the liquid organic hydrogen carriers, the LOHCs, where you basically use an organic compound that can absorb hydrogen. You know, it can easily bond it and you can easily release it. You can use existing infrastructure, pipelines, tankers, to basically use that liquid and transport it and then separate it at the other end and use the organic compound again and start the cycle all over. Doesn't need compression. I don't like it. So, I think like Jeff pointed out, and you see there are so many things going on in the hydrogen world. You know, what to do, what fits best, what works best. I think that's depending on what hydrogen is used for, how it's produced, where we are going with the technology of processing, compressing hydrogen. So it's an exciting time. I think everybody knows that. And like, yeah, that's about all I had to say. I think I'm out of time. I certainly appreciate you taking the time and listening to me. If you have any questions, you can see me at the booth next door. And like I said, if you want to contact Jack to get a copy of the presentation, absolutely. But if you have any questions, suggestions, talk to us. Absolutely appreciate your time. Thank you.